Hi chemists, welcome to part 2 of our rate of reaction discussion. So now we're going to launch into factors that affect rate of reaction, so things that we can change in order to increase or decrease rate of chemical reaction. The first one is concentration, which we've probably seen before. So at higher particle concentrations, more reactant particles will be present. So the frequency of collisions will occur. So you've got more collisions happening more often. And that leads to more productive collisions. So the percentage of collisions that are productive remains the same, but the fact that there's more frequent collisions means you're going to increase the rate of reaction. I like to think about this in terms of a crowded environment. So here I'm thinking of something like a mosh pit where you've got more people in the same amount of space or in a small space. They're moving in kind of random directions, so you're going to have more collisions occurring than if you were kind of going for just a normal stroll in the park or something like that. The second effect that we can talk about with rate of reaction is pressure. Now pressure is very similar to concentration. Now pressure only affects gases, okay? So we're not talking about liquids or solids. If we're increasing the pressure, basically what we're doing is decreasing the volume of the container. So decreasing the volume is going to effectively increase the concentration of reactants. So therefore, it will increase the number of productive collisions, very similar to increase in concentration. So low pressure, we've got gas particles in a certain volume. High pressure, we're effectively reducing the volume, so increasing the concentration, leading to more frequent particle collisions. The next factor is temperature. Now temperature works a little bit differently. When we're increasing the temperature of a reaction, what we're doing is we're increasing the kinetic energy of the reactant particles. So they're more energetic, they're moving more quickly. So what we're actually increasing here is the number of productive collisions, not essentially more frequent collisions, okay? More productive collisions, because a greater proportion of particles are going to have energy greater than the activation energy. Remember, we need to reach that activation energy in order for a productive collision to occur. So this is kind of shown in this graph here. So what we have is the energy on the x-axis. So the further along you go, the more energy the particles have. Up the top of the y-axis, we've got the number of molecules we've given energy. So temperature number 1 is basically saying there are more particles that have lower energy. And as you increase energy going along here, you hit this line which is called the activation energy, EA. So the shaded part here, the green part, they are essentially the number of particles that have energy greater than the activation energy. So when these ones collide, they're going to form products. When all particles in this area of the graph collide, which is the majority of them, it's going to have a non-productive collision. So they're just going to bounce off and they're going to remain reactant particles. Temperature 2 is obviously a bit higher. So what we're saying here is that there's more particles that have a high energy. So we're shifting to the right-hand side in this case. Now what essentially happens is that when you hit this activation energy section, there are more reactant particles that will have that activation energy. So a greater proportion of molecules exceed the activation energy, and this increases rate of reaction, more productive collisions. The next factor is surface area, which is referred to as the state of subdivision. So when you divide, so this is only referring to solids. So when you break up a solid into smaller particles, there's greater surface available for collisions. So think of powder form as opposed to a tablet. We've probably done this practical in previous years. When a solid reacts with a liquid or a gas, the reaction takes place if the liquid or gas can collide with the surface of the solid. Okay? If you're increasing the surface area of the solid, we're allowing for more frequent collisions because a greater surface area of that solid is able to be accessed by the liquid or the gas. So in this case here, we've got a blue solid particle that might be in a tablet form, and you've only got these particles around that can actually collide. The particles in the middle for the solid are kind of trapped. They can't be accessed just yet. So here you've got collisions happening all around, but not in the middle. If we break up that solid and you've got the same number of particles, now this doesn't seem to be the same, but you can see my point. This smaller particle here can be accessed by all of these surrounding particles. So you've got a greater chance of collisions here. Okay, so we've got more frequent collisions. The last factor is a catalyst, and this is a really important concept in chemistry and biology. So what is a catalyst, first of all? A catalyst is a substance that provides the reactant with an alternative pathway that has a lower activation energy. So this is very important. The wording is essential. An alternate, oh, I can't even pronounce it now, an alternative pathway that has a lower activation energy. So what this does is it basically lowers the bar that's required for those productive collisions to occur. So a lower activation energy increases the number of molecules having energy above the activation energy, which is really important. Another important note is that a catalyst is not used up in the process, so a catalyst can be reused, which is fantastic for a manufacturer because we can kind of cut back on costs. If you can reuse the catalyst again and again, that's fantastic. Okay. So here's our energy profile diagram that we've done before. So this is an exothermic reaction, but here we've got a red line which is with a catalyst. So this activation energy here, which was initially quite high, and you might only have a small percentage of reactant particles that can reach that activation energy, now we've got a lower activation energy. So the peak of this kind of curve is lower than here. So that means a greater proportion of those particles can actually have a productive collision to form product. Now, if you're asked about this in a test or an exam, you can't say that a catalyst provides a lower activation energy. Even though that's what it seems like, that's wrong. So don't say lowers activation energy. What a catalyst does is it provides an alternative pathway for the reaction to occur with a lower activation energy. I'll explain that just using an analogy here. So an analogy for a catalyst is basically crossing a mountain. So consider we have this mountain here, and we have two villages on either side of the mountain. So we've got one on this side and one off the back of the picture. Initially, in order to get from one village to another, you needed to climb this mountain. And that took a lot of energy, okay? It takes a lot of work in order to do that big trek to climb over the mountain and get to the other side. So that's our original route for our reaction, okay? But later on, people decided to build a tunnel that went through the mountain, okay? So now the people from both towns were able to access going through the tunnel. Now the tunnel is a lot easier to travel through because you don't have to climb over the top. So that's an alternative route through the tunnel. So that's kind of what a catalyst is doing. A catalyst is providing an alternative route for the reaction to proceed. Okay, so going through that tunnel is much easier. The activation energy would be lower. Okay, now we haven't removed the mountain, so that option is still there. People could still choose to climb over that mountain. It's more difficult, but that option is still there. So we haven't completely lowered the activation energy, but most people are going to use the tunnel. So the easier option is going to be the one that most people are going to choose. So that's very similar. A catalyst provides an alternate pathway with a lower activation energy, but that original route for the reaction to proceed is still there. So the particles can still go over that original route. Thanks very much for watching. Hopefully we learned something about rate of reaction, especially to do with factors and activation energy. I'll see you next time.